Ladies and gentlemen, dear colleagues, I am Miloš Kovačević and I will be chairing the second session of our conference. And in this session, we will have, I hope, two very interesting lectures. Our first speaker is Professor Lidija Zdravković, who is a full professor at the Department of Civil and Environmental Engineering at the Imperial College, London, UK. Her research activities are related to the numerical simulations of the behavior of geotechnical structures and the categorization of thermo-hydromechanical behavior of soils through experimental research. In her presentation, Geotechnical Engineering, Achievements and Challenges over the Past Century, she will highlight the main achievements in the geotechnical engineering discipline since the early 20th century, as well as the current and future challenges. Professor Zdravković, stage is yours.
Thank you very much, Chairman, for your kind introduction. Good afternoon, ladies and gentlemen, colleagues. It is my great pleasure to be here to participate with you at this great celebration and the landmark for the Faculty of Civil Engineering in Belgrade, which is my alma mater institution. I was asked to talk about geotechnical engineering over the past century, as that is my area of interest. And I will start by briefly defining the geotechnical context of the soil itself, what in my personal view have been transformative developments over the past century, the main achievements in the field, and what are the current and future challenges. If somebody talks about soil, probably the first association is with the agricultural use of the soil, but here we're defining very clearly that geotechnical engineering is an integral part of civil engineering discipline, which is concerned with the engineering use of earth materials, soils and rocks for the design, construction and maintenance of natural and built environment. So that is the framework of our considerations. Of course, it is probably fair to say that any civil engineering construction involves the soil in some way, because our structures are supported and rest on the soil via systems of foundations. They're also constructed in the soil, like tunnels and deep excavations, and also constructed from the soil as a compacted material going into earth dams or earthfill embankments. And the principal concern for geotechnical engineers is soil's capacity to sustain construction loads, as well as soil stiffness to essentially limit the excessive movements of the ground that may lead to failure. So that is the scope of what we are interested in. And the main challenges when it comes to the soil mechanics itself, first of all, is the multi-phase nature of the soil being a natural material, not a material that we can make and design its characteristics. It consists, if you look at an element, soil volume, it consists of some solid particles in some arrangement and voids between these particles that are filled in with air or water, or a mix of air and water. And the problem is that any load applied to such a volume of soil is not sustained by a rigid soil skeleton out of these solid particles. There is an interaction between the phases. The skeleton is very deformable, and therefore the behavior of the soil, if we look at any stress-strain relationship, is highly nonlinear. So mathematical formulations of such a behavior are not a mean task. So looking at the development of the design frameworks when it comes to geotechnical engineering, it is probably fair to say that up until the early 20th century, although geotechnical construction was clearly going on, and one of the very early forms of construction were probably flood embankments or piles of clay next to river banks to protect the early dwellings from flooding. However, the formalism in how that is designed really did not exist because of all these complexities in soil behavior. So in the early 20th century, there's some clear laws, physical laws that have been defined to give more of a substance in how we define our calculation tools and our calculation mechanisms for design. And the first is the principle of effective stress that has come from Terzaghi in 1936, defining that any load, any total stress on the soil is essentially transferred through the soil in two parts. One is the part that is transferred through the soil particles, and that is what he called an effective stress. And the other part of the total stress is transferred to voids in the soil through water, if we have saturated soil, and that is what he termed a pore pressure. And then Terzaghi also combined the well-established Darcy's law of flow of water in a medium, realizing that essentially this is governed by the permeability of the soil, so the size of that void space, as well as the pressure gradients here as head expressed in the head H. And this Terzaghi combined into one-dimensional consolidation of soils, which essentially is a settlement of the ground under the pressure differentials. And then in 1941, Biot came along and generalized this theory into three-dimensional theory of consolidation. And both the principle of effective stress and the three-dimensional consolidation theory are really the cornerstone of modern geotechnical practice and design. So at this time, the theoretical frameworks also started to develop, but one has to recognize that this was way before any computers were developed. And therefore, the classical methods of analysis, which are here listed on the left-hand side column, were practically hand calculations that had to satisfy a number of theoretical requirements here, but clearly, because of the complexity of the soil behavior, most of these calculations concentrated only on satisfying the equilibrium between external and internal forces, and were unable to devise the sort of calculation processes to satisfy compatibility and therefore calculate deformations in the ground. And this was only possible if a theoretical framework of elasticity was adopted to calculate deformations in the ground. Otherwise, the soil was simplified as being essentially an assembly of rigid blocks that were moving and failing along the plastic shear zones. And in terms of design, this type of calculation was also limited in what it could provide as a design answer, and mainly it was concentrated on providing information on stability of geotechnical structures, but not so much of ground movements or any effect on adjacent structures and services. And it is probably fair to say that this was the soil mechanics of my undergraduate study here at Imperial, Civil Engineering Department in Belgrade, Faculty of Civil Engineering, in the mid-80s. So where were the main developments then coming from mid-20th century? And this is the personal reflection looking at what is currently happening in the field and where we are going in the future. The first main transformative development has been the advanced laboratory testing of soils to measure both the strength and the stiffness of the soil. Development of something that is termed a critical state soil mechanics framework, which I will briefly describe, and of course, development of modern computers and associated software that eventually enable us to look at the soil as a continuum, and ground as a continuum to analyze. So in terms of laboratory testing of soils, the main advancement have been in the first hydraulic apparatus developed in the UK, and here my current institution, Imperial College, has led the development of laboratory testing equipment with Professor Alan Bishop being at the helm of the laboratory at the time, being able to test cylindrical samples at different initial stress conditions in that triaxial cell, subjected to drained, undrained loading, and subjected to a variety of stress paths. And being able then for the first time to derive strength envelopes of the soil in terms of deviatoric stress and mean effective stress, which are sort of generalized invariants to describe the stress state in the soil, both in triaxial compression and triaxial extension. And this has given then more confidence to this ultimate limit state design as the first sort of design condition to affect the equilibrium. And then another piece of equipment that at the same time was being developed in several laboratories was the so-called hollow cylinder apparatus, which in addition to what the triaxial apparatus was able to do, was able to apply a torque to a cylindrical sample that now had a hole in the middle and enable rotation of principal stresses in an element of soil in that specimen, and therefore give us some measurement of the anisotropy of soil strength and stiffness, but also map the whole of the soil space, not just in triaxial compression and extension, but also in the stress states in between, and produce these more generalized three-dimensional strength envelopes of any type of soil that have subsequently found their application in constitutive models, material models for soil behavior. In addition to ultimate limit states and the failure of the soil, in my personal view, what has made a real breakthrough in dealing with deformations and serviceability limit states in geotechnical engineering has been the measurement of deformation of the soils with the so-called local instruments that are attached to the sample itself, not any longer being attached to the triaxial cell somewhere externally to the cell, and therefore measuring also the compliance of the apparatus as well as deformation of the soil. These are very precise, high-resolution instruments that are measuring deformation of the soil sample itself, and therefore revealing that the stiffness of the soil here on the vertical axis plotted against the deformation of the sample is actually highly nonlinear. It is not elastic. It's maybe elastic at the beginning of loading, but then for the majority of working conditions of many of the geotechnical structures, it is a very nonlinear degradation, which is also dependent on stress level. So this really has enabled huge advancements in the serviceability limit state design, in particular in ground conditions that are dealing with very stiff soils, not soft clays that are essentially failing very quickly, but soils that have high resistance and very nonlinear stiffness. And this was then something that paved the way to develop the first modeling frameworks, proper mathematically formulated modeling frameworks for describing soil behavior. And that is this critical state soil mechanic framework that was based on the experimental data from Imperial College. As I said, that was the main sort of laboratory in the UK and internationally. And the theoretical work was done at the University of Cambridge. And the framework itself was the first one that linked the soil strength and stiffness to the current volume, to that deformation of the void space, which is where the deformation in the soil is happening. And what we were able then for the first time to do, looking at the deformation of the soil and plotting here, for example, the deformation of the volume of the void space and versus the shear deformation of the soil skeleton, we were able to represent for the first time the realistic deformations that we see in most soils, deformation of compression, which is a positive compressive reduction of the void space, or deformation of expansion, which is the expansion of the void space. And the first constitutive frameworks, modified chem clay and chem clay that were developed at the time, have essentially stood up the test of time, and they're still in use today, although with many refinements that have come from these advanced testing of soils that has then been translated into mathematical formulations and implemented within the critical state framework. Of course, none of these two advancements would have been possible if we still had to go away and use those classical methods of analysis where we needed to treat the soil as a rigid material. So this would not be possible to use and advance anything that we have advanced up until today. So development of modern computers and appropriate software has really made huge leaps forward, or enabled us to make huge leaps forward. And the finite element method of analysis has been one that is widely used in all branches of engineering, being developed in the 60s for linear elastic materials in the first instance. It found immediate implementation in mechanical engineering, aerospace engineering, structural mechanics, but application to soil mechanics and to geotechnical engineering really comes a bit later in the first book of Oleg Cienkiewicz that mentions the nonlinearity, that mentions plasticity, that mentions time in soil deformation. And Cienkiewicz is considered one of the pioneers of the finite element method, and subsequent to that first book, several others have come at much later times, specifically related to geotechnical engineering. And this is just an example of the coupling that we are interested in and that we can now analyze in the soil domain, being able to calculate the deformations in the ground, being able to calculate pore pressures, being able to calculate temperature changes if we are dealing with a fully thermohydromechanically coupled problem. And the equations, the formulation here is just an example from a finite element code, ICFEB, that we developed at Imperial College, and that is one of my main tools for research. And the examples that I will show for the rest of this talk are essentially obtained from using this code. So what has this then enabled us to do? So again, I will give a couple of examples of where the main impact has been not only in research, but in practical applications. And being based in London, and London being the most urban city, having very urbanized not only the overground space, but underground space as well. London was until after the end of the Second World War already had a 100 years old network of underground tunnels. So what happened shortly afterwards, at the beginning of the 90s, the first modern tunnel construction was conducted on one of the existing lines, Jubilee Line, and it was known as the Jubilee Line extension, going through quite an urbanized area of London, being conducted with new construction methodology, and therefore being the design needed to really predict quite accurately what the ground movements would be to essentially alleviate and limit any potential for building damage above those new tunnels. And this is where this nonlinear recognition of the nonlinear stiffness of stiff clays, like London clay, came into play, calibrated on the experiments performed on London clay and taken into the finite element formulation and into constitutive modeling of London clay, and showing as one example here the settlement trough above one of the two tunnels at the location of a park. So this was not an urban area, this was St. James's Park, but and looking only at the excavation of the first tunnel that went into the virgin soil, very nice settlement trough measured in the field, but the analysis needed to be conducted before construction, and the analysis showed a very good agreement with the measured data, taking account of this nonlinear shear stiffness, and showing that the usual classical linear elastic soil stiffness, be it isotropic or anisotropic, is clearly deficient in reproducing both the shape of the settlement trough as well as the magnitude of it. But then the real challenge was on the same line at the time, construction of a new underground station at Westminster, which was the deepest excavation of 40 meters at the time, compared to the usual 20-meter deep basements in most buildings. And here the danger was the vicinity of historic structures, the Houses of Parliament and the Big Ben. Masonry structures, as we know, they are very sensitive to differential settlements, and here the finite element analysis was conducted again before the construction to optimize the construction methodology with the purpose of minimizing any movements induced to existing structures. And the picture to the right shows the diagram of the lateral movement of one of the station walls at different elevations of excavation, comparing the predicted and measured movements during the construction. And again, showing that this was very accurate and that the predicted sort of safe construction was fulfilled. So that was one type of problem that was really in the UK became a must for industry. So industry was convinced that that was needed, and industry took it on also in commercial software. The second type of problem that this opened the advancement of computer software and understanding of soil behavior was the ability to look at transient behavior in the soil. Because of the void space, because of the water in the void space, there is, after any construction, there is a dissipation of excess pore pressures, there is a drainage of water from the void space, which causes additional deformations with time. So now we were able to assess also that aspect of design, and where it immediately became important was in problems of infrastructure slopes, because some of these slopes excavated again in a stiff material, stiff clay, like the clays here around Belgrade, so London clay, Oxford clay, and so on, showed instability and failure several years after being excavated. And these are slopes along motorways and along rail tracks. And the question was, why were they failing? And the only way that this could have been shown and demonstrated the reasons for these failures was through numerical analysis. And in this case, the constitutive modeling needed to reproduce this brittleness in stiff materials from peak strength to residual strength, needed to reproduce again the interaction within the soil itself, so the equilibration of pore pressures, and it was clear that the shear surfaces were essentially originating from the toe of the cut slopes and developing gradually, progressing with time until eventual failure. And this particular example predicts failure 14.5 years after slope excavation. So the research here was very much taken by industry, again, because the numerics here was used to quantify stable geometries that industry then used to redesign those slopes and also to redesign any expansion of the motorways or widening of the motorways. And even more recently, a similar type of problem, the construction of the high-speed rail line that is currently going on in the UK, has clearly come from the start of the project with the request for a guarantee of a 120-year design life of those cut slopes. And designers were, again, found themselves in a bit of a conundrum of how to prove this. And again, that was with taking the finite element modeling, taking the variations in the soil, this type of soil, of various stiff clays along the route of high-speed rail, both the shear stiffness, both the nonlinear bulk stiffness, both the permeability of the soil, again, because it's time, 120 years that we need to show, and demonstrating that really what designers were thinking that with a single slope geometry and with depths of the slopes that were varying from 5 meters to 20 meters, it became very clear that the same gradients of slopes cannot be used. And a clear design line of stable slopes is drawn somewhere here. So up to 10 meters deep slopes and mostly 1 to 3 vertical to horizontal gradient are guaranteed to stay stable for 120 years, but other geometries really not. And that caused a bit of a problem because obviously the government has not expropriated enough land to essentially make shallower slopes. So that is why the HS2 has had many reviews and many sort of startups and cancellations, and a number of branches that were originally planned on the route are now not going to happen for a foreseeable future. But this is the answer that they should have probably done at the beginning of the project rather than while everything was going on. So where do we go from here? It is very clear that the whole society is sort of transiting towards sustainable and resilient global society that wants to exploit renewable energy sources, that wants to achieve low carbon economy, zero carbon maybe, but low for sure, that needs to look at this life cycle design, and it also needs to look at the consequences of climate change and how those are going to influence this life cycle design. Clearly, for geotechnical engineering, the enhanced complexity of soil behavior will mean that we have to rely more on numerical tools, because all these thermohydromechanical, possibly chemical interactions cannot be taken into consideration just by hand calculations, so there has to be more numerics. And for that numerics to work and to be sensible, clearly the experimental challenges exist for experimentalists in the laboratory and in the field, because apart from mechanical loading that we have been testing so far, we need to apply thermal perturbations in our triaxial cells, hollow cylinders, and so on, to understand how the soil is going to respond to those changes. So I will again just give a couple of examples before I stop of what may be achievable and where we are moving to. So looking at renewable energy, one of the main sources, at least in the UK and in the Germany and Holland, wind energy, offshore wind in particular, is a very hot topic. And 10 years ago, the industry itself, the offshore developers, realized that they really couldn't move very far with offshore wind because the foundation design for this new type of very large piles, which are called monopiles, that have 8 to 10 meters diameter, but are short, so the length to diameter ratio is about 5, they really were getting very inaccurate predictions of the working loads and ultimate loads using the existing methods of calculation, and these were mainly the so-called PY Winkler type approach for designing the laterally loaded piles. The load here mainly comes horizontally from wind and from wave, and the pile is considered to be a beam, a string of beams supported by lateral springs representing the soil lateral stress as a reaction to this load. So they realized that essentially the reason for this was that these codified design methods were developed for really very slender, so maybe up to 1 meter diameter piles, 20 meters long, that were used for oil and gas platforms in the North Sea and in the Baltic Sea, and therefore doing similar testing now on these large diameter piles would not be possible to derive the new design methods from empirical correlations. So they realized that this will have to be done from some, again, numerical modeling, from 3D finite element analysis. And in about 2013, so the couple of years, the industry was actually getting together to understand what they were supposed to do and how to go about solving this problem, led by the Danish offshore developer Ørsted and the British Carbon Trust and 10 other offshore developers, international offshore developers. They came together to academic working group comprising Oxford University, Imperial College and University College Dublin, with what they named a PISA joint industry project, the Pile Soil Analysis Project, essentially asking for assistance to give some rigor, scientific rigor, into the development of new design methods. And what the academic working group essentially put together was the numerical modeling, the field testing of scaled monopiles that industry fully funded, as well as detailed characterization of the sites where the field testing was performed. There were several sites, and here is just an example of a glacial clay till site at Cowden in the UK, deriving from laboratory and field experiments the site-specific shear modulus, small strain degradation, undrained shear strength that would feed into the 3D numerical analysis. Because the objective was that numerical analysis needs to demonstrate being capable to predict accurately the response of test piles. So this was again blind predictions before the tests were done. And if that is satisfactory, then numerical analysis can be used to derive a new design method. And this was the case, showing again for a Cowden site, the load displacement curves from the field tests, from existing design methods, and from the 3D FE analysis performed during the PISA project, both at sort of ultimate load conditions as well as working load conditions. And having convinced the certifying bodies and the industry who was funding all of this that we can do this from 3D FE analysis, then the real scale monopiles were analyzed, and from those it was possible then to go back to a Winkler type model, but defining not just a single soil reaction from a distributed lateral load, but 3 more soil reactions from distributed moment down the pile, a base shear force, and a base moment. And this industry has taken immediately during the project itself, from 2017, this is an example of their own calculation of the savings in the foundation itself, so the steel, the material itself, applying the PISA design method compared to the existing codified method. So for an average 9-meter diameter pile, the length the codified methods would require is 54 meters, whereas the new design method is 35 meters. And this is from their own calculation of where the savings, the level of savings, which is quite a bit in the money itself, but also in terms of saving in steel, is apparently about 4 Eiffel Towers worth of savings. And this reduction of the cost of foundations translated itself immediately into the cost of the wind energy produced in the UK. And in 2017, that was a big news, headline news on BBC. And not only that, the wind energy sort of halved in a couple of years to what it was in 2015, but also became much lower than the cost of the new nuclear energy produced. So this is again using the complexity to its full of the numerical approach, understanding then what can be simplified, and then simplifying for industry to use a new design method that has made it all efficient and possible to actually make the change to the society itself. And I'll just use one more example of renewable energy, which is not yet at that stage of being fully sorted out. And this is a use of geothermal energy to provide low carbon and reasonably cheap heating and cooling of the internal spaces. It relies on the fact that the temperature of the ground itself, from about 10-meter depth onwards to about maybe 200-300 meter depth, is constant throughout the year. And therefore, what is utilized here in what are termed here ground source energy systems is a difference in temperature between the air temperature and the ground in winter and in the summer. And in the winter, the heat exchanger fluids in the pipes installed in the ground are essentially warming up the fluid and passing it to the building for heating, whereas in the summer, the heat is taken out and stored in the ground, so it is being cooled in the ground and taken back into the building for cooling. And the beauty of this is that there are two systems for this to be installed, open and closed loop systems. The closed loop systems can actually be installed in structural elements like piles that support the building stability, or retaining walls or tunnel linings, and have a dual purpose. The problem, however, is that these elements would then go through the cycles, seasonal cycles of heating and cooling. Ground will be heating and cooling seasonally, and therefore the problem is the effect on what is already there in the ground. Existing foundations that are not thermal, tunnels, and so on. And these graphs here just show, for example, a retaining wall here that is made thermoactive and heated by additional 15 degrees centigrade, causes obviously thermal expansion of the soil that imposes some deformations and extra forces in the structural elements. But the bigger problem is that the water in the soil, water in the voids, has higher thermal expansion than the soil skeleton, and therefore induces excess pore pressures as well, which then reduce the effective stresses and therefore the resistance of the soil. And that clearly can cause additional deformations in the soil. So this, as I said, is still very much a matter of research. So that is one of the things that is there for the future, because we need to understand, first of all, the soil behavior, the limits of the soil strength and stiffness subjected to these thermal cycles, but also what it induces to existing structures and services, and whether there is possibility for them to be damaged. And this is, again, one of the things that are currently happening and are being investigated. Clearly, infrastructure is always an issue. Aging infrastructure, not only in the UK, here in Serbia as well, that all is, needs to be extended for future use. The life cycle assessment is very much there when it comes to geotechnical engineering because of this multi-phase behavior of the soil. So, in my personal view, the geotechnical design faces increasing complexities because of the problems that are being, appearing there to be solved for the society. Design solutions will need to continue to be addressed by robust and sophisticated numerical modeling because of these complexities. But as I already pointed out, the numerical input really needs to have appropriate and adequate characterization of the soil behavior to provide adequate answers. And the field monitoring of live projects is really where the value of the whole undertaking is for the purpose of validating the numerical models, because all of these are predictions in the long term. So if we can validate our numerical models on the live projects, then we gain further confidence in our future predictions. And my last slide really is this sort of vision of interaction between laboratory and field testing of soils, predictive numerical analysis, and field monitoring and sensing, feeding constantly into each other to essentially make sure that what we do is sort of safe and economical. Thank you very much for your attention.
Okay, Professor Lidija Zdravković, thank you for your review of current trends in geotechnical engineering. Are there any questions from the audience? Yes, Mr. Hooling. Mr. Hooling.
Okay. Thank you very much for a very clear and very interesting presentation. I learned a lot because I'm not in geotechnical engineering, but I have two questions and they're related, and I think there's also maybe, a possibility to work together basically, because for example, when you talked about the soil testing, I noticed that the soil sample that is analyzed is actually quite small, and we know that the soil is not homogeneous, it's very heterogeneous. Sure. So surely if you take a sample 5 meters away, or it would have different properties. So you would like to take into account the spatial variability. So do you know of any research or publication? Is that routinely being addressed, the spatial variation, for example, using geostatistical methods?
When we conduct our testing, we do take specimens of soil from various depths and from various locations on the site. So yes, I think from the few graphs that I showed of the soil data, you will see that there are a number of lines. And yes, we do have to perform interpretations of what we believe is the best sort of estimate of strength, of stiffness, and so on. But there are, in the finite element method itself, there are moves to use so-called random fields, finite elements, where, yes, that sort of randomization can be taken into account. Unfortunately, it hasn't taken up by industry, because that is, I think, another level of complexity that industry obviously probably can't accommodate yet at the moment. But also, what is the governing reason, I think, for doing more statistical approach on the soil data is the volume of the data that we get. So if you think that we may have maybe 30, 40 triaxial tests performed on a site, then that would really cause quite a bit of maybe skewness in the data if we just go and try to look at average value, like purely statistically, just find average, mean, and so on. So what we do tend to rely is, at the moment, not really statistical unless we have large quantity of data. That is the issue.
Thank you. Yeah, in a way, you already answered my second question, because I noticed the modeling is quite advanced, but it's really physical deterministic.
Exactly, it
and
is.
so I was indeed asking myself, maybe you also take stochastic modeling approach, so you mentioned random fields, so you could, for example, do, and probably, but maybe industry is not taking that up, but you'd like Monte Carlo types of analysis.
Sure, absolutely. All of that exists, yes, exactly. But when you think of for example, if we're talking of clays, one triaxial experiment can last 2 or 3 months. So you can't perform very many experiments for a project to perform, to have a characterization of, I don't know, 100 or 200 test data to work with.
Thank you. And I think it was also very nice that you're involved in a project which has an acronym PISA. That was very interesting.
That was a bit strange to us when they came with that acronym, but yeah.
Thank you.
Thank you.
Congratulations, very good presentation, very good overview of what is happening.
Thank you.
I'm interested in the vision now on what are some future challenges, in particular the field monitoring.
Mm-hmm.
Again, I come from pavements, from roads. Say it again? Louder. Can you hear me now? All right. Sorry. And as I was saying, I'm interested in field monitoring in roads, infrastructure.
Okay.
And as other colleagues are now working on, we are going toward structural health monitoring with some sensors, possibly by using BIM as a platform. So I was wondering, is there any soil information modeling happening? No? Some digital platform, some digital twin of the soil where you can insert all this data-driven approach that is now happening?
There were attempts for soil. It's a bit difficult for soil because it is a natural material, and therefore you can make maybe classification on a type like stiff clay, over-consolidated clay, normally consolidated clay, and so on. It is not straightforward, but there are BIM obviously in industry has taken up, and there are the collection of data. I mean, every major project, maybe not small projects, but major projects will have a ground investigation that will be stored into BIM platforms. How they use them, that is a different story, really. And because, again, depends on how the data is interpreted and whether it is adequately or not adequately interpreted, whether the tests are done correctly. Sometimes commercial laboratories are not as precise as research laboratories, but the BIM is there. What else is there in terms of field monitoring? Increasingly is INSA technology and satellite so reconnaissance of the ground surface. That is a bit crude for obviously looking at in depth what is happening with the soil, but it's fine for the ground surface. And for example, the cross-rail tunneling that was recently also going on in London as a latest tunneling project was very much monitored. The London Basin, the whole of the London Basins was very much followed by INSA technology, and was able to show the red patterns where settlements of the ground surface were notified, obviously, during the construction.
Thank you. May I ask you another question?
Of course.
Yeah. you mentioned some technology for measuring, and I'm now working, can you hear me? Yeah? I'm now working with people developing sensors, and they always asking, what do you want to measure?
Sure.
In the case of slopes, no? What do you think we can measure now, and what would you love to measure if you could?
With slopes, with anything that is really has to do with the ground, I think the main measurement are the pore pressures. So the pressures in that void space, because that is where the most of the movements are happening. For example, you excavate a slope, the initial phreatic surface depresses, and then with time it wants to go into some steady state equilibrium. And that is where the failure can be or cannot be initiated. So if we could have in slopes a continuous measurement of pore pressures, I think that would do a lot for any sort of early warning. But it's something that you need to convince industry that it's worth putting in and monitoring for a long period of time.
Thank you.
Okay, thank you. Okay. But please, we are short in time just. Okay, thank you.
I have a very, very simple question. How you feel about the relationship of the actual state of field measurements and laboratory experiments?
I think they have to be integrated with each other. So with the field measurements, it's much easier to get the profile, the ground profile, like CPT, so cone penetration testing, for example, or geophysical monitoring. We can get a continuous ground profile of what is there underneath our feet. And that has a value on its own. There are some correlations that we can use to interpret the direct design parameters that we need, but using that immediately in design, I would not necessarily go forward with that without checking with a localized sampling and testing in the laboratory as well. So approach for me would be integrating both, not going one or the other, because they both have a value and they sort of feel the information from one to the other where the gap exists.
Presently, you are very satisfied with the results obtained from the field and laboratory experiments.
Depends. Okay, depends on the who is conducting experiments, but looking at where it all is going. For example, offshore industry inevitably is moving to just field experiments, although they do take samples from the seabed. But to get the profiles over the whole area of a wind farm, they just go with the CPT tests and make their decision on what ground profile there is. So I don't say that I would go one way or the other. My approach is to look at the evidence that is there and then make engineering judgment on what to use and what not to use. There has to be. This is why I'm saying just doing statistical analysis often doesn't work, because you have disparate sets of data, averages, can be anything.
Okay, I am agreeable. Nothing without a judgment.
Absolutely.
Okay. Thank you once again for your interesting presentation.